Maybe we get started. Good morning, everyone. Welcome to another Terasaki seminar series. Today, we have Professor Jun Chen. He's currently assistant professor in the Department of Bioengineering at the University of California, Los Angeles. His research is about nanotechnology and bioelectronics for energy sensing, therapeutic applications in the form of smart textiles, wearables, and body area networks. He has published 2 books, 240 journal papers, 100 of them being the corresponding author. The journals include Chemical Reviews, Chemical Society Reviews, Nature Materials, Nature Electronics, Nature Communications, Science Advances, Advanced Materials, and many others. He has filed 14 US patents with a current H-index of 85 and 45 ESI highly cited papers. Dr. Chen was identified to be one of the world's most influential researchers in the field of material science by the Web of Science group. Beyond research, he is an associate editor of Biosensors and Bioelectronics and advisory editorial board members of Matter, Nanomicro Letters, Materials Today Energy, Cell Reports, Physical Science, and Innovation. He has won numerous awards: BBRF Young Investigator Award, ACS PMSC Young Investigator Award, Materials Today Rising Star Award, Advanced Materials Rising Star, and many, many others. The floor is yours, Professor.
Okay. Thank you very much for Arnie and Mehmet kind invitation and good organization. It's really my great honor to be here to give a talk for the Terasaki Institute for Biomedical Innovation. So I'm Jun Chen. So today I would like to share with you a story entitled Smart Textile for Personal Healthcare. So first, why we need a personal healthcare? Let's look at this curve. This curve actually describes the relationship between the disease burden with the cost. So our current healthcare system based on a typical intervention. That means if you have a head, for example, if you have symptom, for example, if you have a headache, then you will call your doctor to make an appointment. Maybe the appointment will check their schedule, said maybe the earliest available time is tomorrow afternoon. So you at that time you have to drive a car to a clinic center, and then they will give you some treatment. So you can see this current healthcare system, they have some disadvantages. First, that's based on disease management. We have suffering from the bad feelings such as the headache. And also it's a very high cost. High cost means we need to spend more time, effort, and money to get us back to a healthy state. And also it's very low efficiency. The efficiency means in doctor-patient efficiency. So for example, I have to wait for 1 or 2 days, then I drive 1 or maybe nowadays in Los Angeles have very heavy traffic jam, so you have to spend maybe 1 hour on the way. You drive to clinic center, and then they will give you some treatment, maybe just 20 minutes or 10 minutes. You can see this kind of doctor-patient efficiency is very low as well. So to solve this problem, I have been thinking about if we can perform this kind of early molecular detection. For example, if I have a body temperature sensor, it's constantly reporting my body temperature. If this morning I wake up, I found that my body temperature is abnormally high compared to my historical data, maybe 1 week ago, 1 month ago. So that shows that, that indicates that I may have potential get a headache. So probably I just share this information with a doctor over distance, just give a phone call or send an email, or just give a text message. So the doctor will give me immediate care, or maybe he or she will give me some suggestion. Dr. Chen, as assistant professor, you may have a lot of stress or pressure. So maybe now you just slow down a little bit, drink some hot water, and take a good sleep. Maybe the headache will not come to me. So this is a concept of personal health care. you can see that's basically based on the health enhancement and disease prevention. So, and also definitely high quality, because I don't need to go through this headache, this type of bad feeling, and also it's no cost. I may just need to slow down a little bit, drink some hot water, take some good rest, then the headache will not come to me. So you can say this type of healthcare transformation is very important, but to realize this type of healthcare transformation, we definitely need a lot of wearable biomedical devices or implantable biomedical devices like the body temperature sensor to constantly provide our physiological information. So I think to realize this type of healthcare transformation, we have to develop some wearable biomedical devices which has affordable price and also is convenient or comfort to wear. If you wear it and if you feel discomfort, maybe people will feel reluctant to wear such type of devices. So how to develop those precisely affordable and also wearing comfort biomedical devices is gonna be a challenge. So Apple Watch is one of the most famous one actually nowadays. So you can wear the Apple Watch and then you can read out your heart rate all the time. So definitely this type of device has disadvantage. For example, is additional burden to wear. For example, especially for our scientific researchers, we have to type in a lot on the keyboard. So if you wear a watch, definitely it's gonna be inconvenient and also very expensive. So this single Apple Watch may cost about $1,200 something. So with this pen, actually, I have been thinking about can we develop our textiles into wearable biomedical devices, because textiles definitely they have great wearing comfort. For example, if you constantly wear a clothes for maybe 1 month, no, you will not feel discomfort or what, you will not feel a discomfort either. So that means actually, definitely they have very good wearing comfort, and also they have very good scalability. So you can use textile weaving or latent technology to build up those products at a larger scale. Actually, human beings have a long history with textiles. Textiles itself have a number of advantages to be developed into wearable biomedical devices. For example, they have a wide range of materials used from natural materials, silk, wool, cotton, to synthetic material. For example, some polymer, peptide, polyimide, polyester, and actually a lot of them actually are biocompatible, biodegradable, even bioabsorbable. But look at those materials. If you want to develop those materials into electronics devices, for example, bioelectronics. So definitely there are challenges over there, because for the including this natural materials or synthetic materials, all of them actually, most of them actually are non-conductive and also is chemically inert. So if you wanted to develop into electronics devices, definitely there will be challenge over there. To solve this problem, actually, I noticed that the human body contains a lot of different types of biomechanical motions. For example, when I talk to you, I'm breathing, my heart is beating. So actually, we have a lot of biomechanical motions, biomechanical activity over there. So I have been thinking about if we use textiles to convert those type of biomechanical motions into electricity, so probably we can use those generate electricity for energy sense and therapeutic applications. Then we have a possibility of developing those textiles into our biomedical devices. So very recently, actually, in March this year, the editor-in-chief of Nature Electronics invited us to write a comprehensive review talking about smart textile personal healthcare. So actually here I would like to share the first figure of this review paper share with you. Basically, the figure one is talking about the timeline platform technology developed for smart healthcare textile. So especially my contribution to this figure is those two platform technology. One is pure electricity that is invented in 2013. Another one is magnetoelasticity that is our group at UCLA invented in 2021. So basically today's talk, I just wanted to use those two platform technology to show you how can we construct smart textile for power supply for biomonitoring and for therapeutics. So for triple electricity here, I would like to use one slide to introduce that to you. How does it work? So basically, triple electricity, this platform technology is based on a very old phenomenon, that is the contact education. So when we are very young, we're educated that when you use that glass, the friction with silk is generate static charges. Actually, we can use the static charge to attract small items. Or in the cold winter, when you take off sweaters, you can see the sparkles in the darkness. So all of those are because the closed materials have strong contact education with your skin, so they will generate static charge over there. So basically this working mechanism was invented a new platform technology we call triple electric nanogenerators, TNG. So basically it's able to convert mechanical motion into electricity. How that works? Here's a video to show that. So so basically, if there's a two polymer material, just like a blue layer and a purple layer, so if they have different electron affinities, when they contact with each other, charge transfer interface with the result, one will be negative charge, another will be positive charge. So those charge actually static charge can sustain a surface for a long period of time. So if we coat a power metal electrode at the back of the two polymer layers, so basically as the mechanical motions to induce a periodical contact separation procedures between the two charged polymer layers. So they will induce fluid electrons, flow back and forth in the back of metal electrode. So by doing it, they're able to convert the biomechanical motion or mechanical motions into alternating current or voltage signals. So basically, we can use those electric signals for energy sensor therapeutic applications. So actually, in the past 10 years, this field is growing very fast. And last year, 2021, the pioneer researcher, Professor Jun Chen, wrote a review on the nanogenerator field, and I'm lucky to rank the #2 in the world in terms the influential or the contribution, scientific contribution to the community. So this is one of the platform technology I will used in my talk today. So another one that is magnetoelastic effect. That is a recent platform technology I built up at UCLA, and we are pioneering this research field. So basically, we are using magnetoelastic effect to construct some soft bioelectronics. So the fabrication procedure could be very easy. So we just mix some magnetic powders with some soft polymers. So we are showing that. So when we apply mechanical force to those soft composites, that will induce magnetic field change. So we just put this soft composite as a mechanical magnetomechanical coupling layer. We call it MC layer. So when you apply mechanical force, that will induce magnetic field change. So this magnetic field change could pick up by some magnetic induction layers. We call it MI layer. So this induction will induce some electricity generation as well. We can also use this generate electricity for energy sensor therapeutic applications. But a big advantage of this technology is because the magnetic field could penetrate the water molecules. So basically, the device is intrinsically waterproof. That's going to be very useful if you wanted to develop some wearable or implantable bioelectronics. Because on human skin, we have a lot of perspiration. In the human body, we have a lot of biofluid. So we definitely need that device to be waterproof. So this one actually, this platform technology is very advantageous. That's because it's intrinsically waterproof based on this working mechanism. So with these two platform technology, I just want to show you in the following slides, how can we use those two platform technologies to construct smart textiles for sensing therapeutic applications, sensing therapeutic energy, that's power supply applications. Let's go to the first category, that is for biomonitoring. So the very first application scenario I want to share with you, that is for we are using those textiles for sleeping quality evaluations. So actually, sleeping disorder is a major health threatening in high-paced modern society, which could result in mood disturbance and many heart-related diseases. For example, someday in the future, if your partner gets mad at you, maybe it's not because he or she has bad personality, just because he or she is actually going through a sleeping disorder. So current technology for sleep disorder detection, we have two platform technology. One is polysomnography. You can see we have to use a lot of wells and clinicals to clamp the fingers. And another one is cell phone APP. Basically during the sleep, actually, you just put a cell phone on your bed sheet. So there's an APP inside. They can detect the body movement and then to indicate that you're in a sleeping state or in an awake state. But definitely those technologies have disadvantages. For example, they have very complex structure design and they're very high cost. And also is very inconvenient to use. For example, especially this polysomnography, these ones you have to use wells to wrap up on your body. Maybe that will make you feel disturbed and maybe make your sleeping disorder worse. And also not enough accuracy, especially for cell phone APP1, because the bulky structure of the cell phone sometimes is very insensitive to the body movement during the sleep. So to solve this problem, we just develop a pressure-sensitive, large-scale smart bed sheet. Basically, you can see that the bed sheet could be large-scale fabricated. So each of the bed sheet we have triboelectric sensors. So those sensors based on the contact some, so it's very sensitive to the body movement. So when people sleep on the bed sheet, the body movement, even the some finger bending, this type of biomechanical movement could be detected and generate electricity. So the working principle could be very easy. So we just use two conductive fabric as a top on the top and bottom layer. In the middle, we just have a economical available PET wave-shaped plastic materials. So basically, when human body apply pressure to the device, and they will induce a contact area change between the PET and the conductive fabric. So with the result, they will generate a relative high voltage electric signal. For example, this electric signal, when you use just finger to touch this smaller bed sheet, you can see they can generate a voltage up to 3.5 volt. So we just analyze the amplitude and frequency information of those electric signals. We can construct this type of body movement during whole night sleep. So look at the data. Here is the sleep quality report we delivered. So you can see we are using the body movement amplitude as a classifier. We can see that people could be in four sleeping state. One is awake sleepy state, light sleepy state, and also deep sleep state. So actually, this monitoring is continuous. Basically, for the participant, when he or she goes to bed from 11 p.m. and wake up to 8 a.m., you can see basically according to the body movement, we can see that the participant has a deep sleep actually at about 2:30 a.m. in the morning with a time span 3 hours. That means actually this participant is very lucky. He or she doesn't have a sleeping disorder. So we actually, those three-layer structure design actually is not washable. So in order to make the textile, in order to make the bed sheet washable, so recently we developed another single layer, the ultra soft washable smart textile. Basically, the construction very simple. We just purchase a piece of commercialized available textile or substrate. Then we just insert some functional fibers onto it. This is a real photograph. You can see the scale bar here is 1 meter. So you can see this device definitely could be large scale fabricated. So basically for each of sensor unit, we just integrate some functional fibers. So the fiber, look at here, we just use some polyester twisted against the metal yarns. And in the outside layer, we have a silicon tube to seal the whole device to make it waterproof. And this device is demonstrated that when we put a piece of device into a tank of water, so as long as you can input some mechanical pressure to the textile, you can see they can still generate voltage signal up to 0.7 volt. So basically, we can use those generate electric signal to indicate our sleeping behaviors. So for the clinical application, we just use them to diagnose the sleep apnea. So what is sleep apnea? Actually, some people may stop breathing during sleep. If you failed to timely wake him or her up immediately, it may cause death. So basically, use this textiles, we can provide intervention to such type of diseases. So we just cover this textile on the belly of the people. So just like a bedsheet and a cover on a human body. So you can see during regular breath, because your belly is up and down, they can generate regular electrical signals. So once the participants stop breathing, actually you can see they will have large fluctuation in output electrical signals. So basically, we just develop those fluctuation signal as a warning signal. Actually, you can either trigger a phone call to notify his or her family member, or just notify doctors, or trigger alarm. So to wake this people or this patient wake up. Otherwise, if he or she has long time in a long breathing state, it may cause death. So basically, we can just use textiles to monitor and provide intervention to the sleep apnea. So actually, textiles cannot be only utilized for sleeping-related studies, could also utilize for cardiovascular monitoring as well. So here's one of another design. We just use some functional fibers, especially we use electron spinning to mimic the human muscle fibers. So then we'll construct long-woven textile. Then the textile actually is also very sensitive to the external pressure. Look at here, those photograph of the device. So basically, we just attach a device to the leg artery, so they can constantly convert the pulse waves into electric signals. So those are generated current peaks. So basically, we just calculate the number of peaks and divide by time, then give us a heart rate. You can see we just attach this device to leg artery side. The device could be just 1 centimeter by 1.5 centimeters. So it's very tiny one and very lightweight. So you can see before and after exercise, the heart rate increased from 73 minutes to 92 minutes. So basically, they can constantly provide our heart rate data. So for this kind of long moving textiles, there's a disadvantage that it doesn't have much good breathability. So in order to solve this problem, recently we developed another fabric-based textile devices. It is also able to convert the pulse waves into electric signal. So basically, the structure design is very easy. We just use the silver-coated fabric substrate. On top of that, we just construct a flower-shaped device structure. So that for the flower-shaped device structure, we will still use polyester, metal, nylon, those polymer materials. You can see those materials definitely are very economically available, not very expensive. So basically, the working principle could be very easy for each of the functional yarns. If we give a large view, you can see basically we just use some 3 polyester yarns to twist against the metal yarns. So those devices are also very sensitive to the pulse vibrations. It's able to convert the pulse vibration into electric signal. So the working principle could be illustrated here. So these are the cross-section view of the 3 polyester yarns. In the middle, this metal yarns. So during the blood vessel is construction expansion. So basically, they can also induce a contact separation between the silver and the polyester, and with the result, they can also generate electric signal in the internal circuitry. So basically, when we weld this textile device against our waist artery site, you can see those generate a voltage signal constantly in different cardiac cycles. If we take a large view, one cardiac cycle, basically look at here, the 3 tipping point, PSP and PD could be clearly read out. So those generated electric signal actually are analog signal. So if you wanted to connect them to cell phone app to build up a user-friendly interface, we still need to go through a number of single process and transmission. So basically, those generated analog signal we have going to filter, amplifier, and then we have going to analog to digital converter. That's ADC convert. And then we still use some microcontrol unit and a Bluetooth. So finally, you can see we can wirelessly transmit those generate electric signal to the cell phone app. So in the future, you just look at a cell phone app, you can constantly read out the possible profiles. So if you found some abnormalities, then you can just do a screenshot or just send out a text message or give a phone call to share with your doctor immediately, so then they can give you some suggestion or take some actions. So definitely some of the cardiovascular diseases may not come to you because you will realize those disease potential at a very early stage. So here's a video to show that. So it's operation procedures. Look at here, basically it's a Textile product. So here is some circuitries. Here is a wireless receivers. So basically, when you wire this type of textile devices, you can see your pulse waves can be constantly displayed on the desktop. So basically, all of your pulse wave velocity, blood pressure could be timely or dynamically calculated and displayed. So basically, here basically we can definitely we can use cell phone to replace this desktop. While we use desktop here, just wanted to give you a clear view about the pulse wave profile. So that is one of the Textile products for cardiovascular monitoring. So that is a triple electricity platform technology. Actually, now comes to another very exciting platform technology we invented at the UCLA. So that is we call it discovery magnetoelastic effect in soft system. So what's magnetoelastic effect? So this effect actually is discovered by Italian physics scientist. That is we call Valery. So we can also call it Valery effect. So what is that? So in 1865, they found that in some metal alloy. So when you apply mechanical pressure, look at here. So when you apply mechanical pressure up to 20 megapascals to those metal alloy, they will induce magnetic flux density change. So when you increase the pressure, the flux density will decrease. So when you release the force, so the magnetic flux density will back to normal state. So you can see this phenomenon in the past 150 years can only observe in metal alloy. So very recently, we just mixed some magnetic powders with soft composite. We show that we can also observe this magnetoelastic effect. Look at here, basically when we apply mechanical pressure, just about 150 kilopascals, so much lower than this 20 or 40 megapascals. We show that in this soft composite, we can also observe magnetic flux density change. So when you apply mechanical pressure, so magnetic flux density will decrease. When you release the force, so definitely the magnetic flux density will back to orange state. So this work on recently published on Nature Material, highlighted on the front cover and also highlighted by Nature as well. So just based on this working principle, recently we construct another type of waterproof, biocompatible textiles, so which is also able to mirror the pulse waves. But the big advantage is that those devices could be operate in a water situation. So you can see, which is where a piece of textiles, even underwater situation, it can constantly convert those pulse waves into electric signal. So look at here, this is the electric signal for 1 cardiac cycles. So no matter is with heavy perspiration or even underwater situation, basically we can analyze those general electric signal to monitor our cardiovascular parameters. So we also to test the biocompatibility of the device with support for Professor Song Li. So we just culture some type blood cells on the devices. You can see basically those devices is actually very compatible compared with the control group. So we still similarly, we just wear this piece of textiles, we can constantly read out our pulse wave profiles and give out a lot of cardiovascular parameters, including the pulse wave velocity or some other heart rate or some other cardiovascular parameters constantly, even while in a heavy sweat state or even in an underwater situation. So with this platform technology, we are showing that they can also contract into a textile for breath monitoring. So we just put this type of device on the belly part. So you can hear this real photograph in the lab. So we just weld this piece of devices here. So when you breathe, definitely they can convert the respiration. This can be kind of motion into electric signal constantly. So here is an electrical profile accordingly to different breath situation. For during the normal breath or during rapid breath, if you have a coughing, basically you can see the electric signal in different waveforms. We can analyze those waveforms, including the frequency information, the shape, and also the amplitude. Then we can monitor our respiration situations. So we also showing that this device could be used for waterproof human-machine interface. So basically, we just wear this type of device on a human body, though. So we just use finger touch the different units, so we can use them to control music players. So basically, when you touch different the unit, then we can play or pause or play next song or last song. So basically, we can use this control this music player. So basically, use this type of platform to construct our human-machine, wearable human-machine interface devices. So we can also use this platform for implantable devices. So here is one of the design. We just use some liquid metals or the magnetic induction layer. So basically, you can see the whole device is all-in-one body design, and is also intrinsically waterproof. So we're showing that in order to increase the biocompatibility of the device, because some of the magnetic powder is not biocompatible, so we just use some silica coating on the magnetic powder, you can say, to make the whole device to increase the biocompatibility of the device. So we are test them in vivo in animal model. So basically, we just put a device on the heart of the mouse. You can see definitely we can monitor the heart beating. This electric signal to describe its destiny or systole, this kind of electric signal. Definitely with this kind of fine design device, and also for implantable measurement, we can get more detailed information regarding our heart beating. So actually, for those wearable biomedical devices which relies on convert the biomechanical motion into electricity, so for those type of devices, we call self-powered devices, and they definitely have disadvantages because those devices cannot only convert the pulse wave or respiration or finger movement or those finger touch, those mechanical pressure into electricity. They can also convert the body movement. For example, when you're walking, so they will input some mechanical pressure to this biomedical device as well. So that means those devices have not a motion artifact. So this is a common challenge in that field. So recently we just use machine learning to describe to solve this problem. Basically, you just use a textile-based devices well against the artery site. So the device is actually just very simple. We just use a textile layer, and then we use some carbon nanotube coated cotton fibers as a cotton layer as one of the electrode, and then we use FEP as one of the functional layer, and then we use aluminum as another electrode. Then we use PDMS as a substrate. So those devices actually is waterproof. It's able to constantly convert the pulse wave into electricity. But here we use some machine learning algorithm to get rid of the motion artifact. For example, when you wear this type of device, when you bend your arm, so basically this bending of the arm can also induce electricity. So basically, with the assistant of machine learning, we're showing that even when wear this type of device, when you play basketball, when you walk in, so they can constantly and accurately read out our blood pressure. So look at compare with the commercialized devices. So the accuracy of our textile devices actually is comparable to the commercialized cardiovascular monitor. And in the future, it's well this piece of textiles, and actually you just take our cell phone, even you're walking, you are play basketball, you can also read out your pulse wave profile as well. So, and because the COVID now become very popular, so we still use those sensors to detect the respiration monitoring, just develop an unmask sensor network. So look at here, we just engineer our commercialized facial mask. We just deploy five sensors to the facial masks. Those sensors very sensitive to the flow dynamic when you during the breath. So look at here, which is this type of a commercialized facial mask, basically 5 sensors corresponding to 5 channels electric signal. So they actually, with the monitoring results from the 5 channels of the 5 sensors, actually we can give very accurate monitoring of flow dynamic during the cavity between the facial mask and your mouth area. So we still use the amplifier and the set and also filters and also machine learning algorithm, and eventually you can display it on a cell phone app. So basically look at here, so those facial masks, they can accurately detect the different breath situation, including normal breath, deep breath, when you cough or when you're talking. So basically with different breath situation, those facial masks could definitely monitor our breath behavior. So if you have a COVID, maybe your respiration going to be very shallow and very high frequency. The output signal could be very have smaller amplitude but higher frequency. So basically, we just analyze those 5 channel electric signal to monitor different respiration situations. So this is something about the biomonitoring. So for therapeutics, we can also use some textiles to make a contribution to this community. So here I just considering time issue. Here I just want to give you one example. That is how can we use textile contribute to assistive physical therapy? Actually, 37.5 million American 18 or older reported trouble hearing, and actually 75 of them are in an employed state. So in order to promote the communication between sender and non-senders, so recently we developed a wearable text glove which is able to perform sound-to-speech translation. Look at here, this is a text glove. Actually, they have 2 components. One stretchable sensor unit, another is wearable flexible PCB, the printed circuit board for singular processing. So the stretchable sensor unit is responsible to convert this kind of finger spelling biomechanical motion into electricity. So the wireless flexible PCB is for singular processing and transmission. So we're showing that those devices actually is made of polymer layers. For example, here we use some PDMIs, polyester metal yarns. So we just use 6 polyester yarn to twist against them 1 metal yarns, and then we use the PDMS at the outer layer surface because PDMS is very soft and biocompatible. And also the whole device is constructed onto fibers to make the whole device very stretchable. So definitely when you wear those type of devices and perform sound-to-speech translation, they are able to convert different this kind of finger spelling into electricity. Look at here, those are generated electric signal from 5 fingers. So if you perform standard American Sign Language to express numbers, letters ABC, numbers 1, 2, 3, or short phrase I love you. So basically, with different finger spelling, you can see they generate different electric signal. So we just use those electric signals as the recognition patterns. We are showing that when you wear this piece of text gloves and perform sign language, so they can place out the voice. So those are another view of the user interface in a cell phone app. So here is a video to visualize its operation procedures.
I L Y I love you.
So you can see for the translation that certainly have some delay. So in the future, probably will use some high computing power chips and to increase the calculation speed. Definitely the delay will be reduced. So this work is when it's published in 2020, actually received more than 200 million coverage in the world, and also Science read a paper to highlight this work, and also is put as a top 10 science story of 2020 by the OSC, and also is put as a automatic top 100. So the automatic checked more than 3.4 million works published on 2020 across all the 20 subjects, and this article made the top 100 most discussed article by their data analysis. So that's one example for therapeutics. Last one is the energy. So people may think, why energy is a portion of smart textile for personal health care? But because look at here, this is the wearable circuitry for biosensing. This is a wearable ultrasonic sensor for cardiovascular monitoring. So definitely for those biomedical devices, they need a power supply, and it's beyond the capability of a battery system. Look at the photograph here. These are typical batteries. You can see they have very rigid structure design, and then they are made of toxic elements, and also they can release heat during the discharging procedures. That may cause people feel discomfort if you wear it or if you implantable, if you integrate into implantable devices. So to solve this problem, I have to think about actually textiles on human body or in surroundings. We have a lot of renewable energy sources. If we are able to use those textiles to convert those renewable energy sources into electricity, maybe we can sustainably drive some smart electronics. So typically we have solar radiation and molecular deformation. So when you wear clothes or work under sunshine, so those energy sources actually are immediately available to you. So if we could use textiles to convert those renewable energy sources into electricity, definitely we can use them to constantly drive some small electronics. So here's one of the solutions. So we just invent hybridized textiles, which is able to simultaneously convert the biomechanical motion and solar radiation into electricity. So here for the biomechanical motion energy harvesting, here we just use a piece of a triple textile is able to convert this kind of closed deformations in mechanical pressure into electricity. So for solar product, we just use a Dyson set solar cell, use a Vivian technology to contract this piece of solar textile. They are able to convert the solar radiation into electricity as well. So when we integrate those two components into a clothes, so you can see here are the experimental data. So under 1 cent condition, with a size of the device 4 centimeter by 5 centimeter, just about the size of half of a human palm. So you can see with under 1 cent condition, those hybridized power textiles are able to deliver power up to 0.5 milliwatt, and a wide loading resistance from 1,000 ohm to 1 mega ohm. So definitely the output power could be greatly improved if we increase the size of the device. So here, if we increase the size of the device, so under 1 cent condition, you can see under the this textiles are able to directly charge your cell phone. And here, so with a small piece of textiles, so wear against on your arm. So when you wave your hand under the sun, you can see this electronic watch could be constantly driven. So certainly in the future, we can use those. You can use those generated power to drive some wearable biomedical devices to realize functionality. So actually, textile for energy harvesting is not limited to for biomechanical energy and solar energy. It's also could able to harvest energy from body heat or biochemicals. So definitely 2 years ago, so the chemical review invited us to write a very comprehensive review talking about smart textile for electricity generation. So this paper was already cited more than 450 times. So if you're interested in this topic, please read this paper. I think it's going to be very comprehensive and inspiring. It includes 800 references. So actually for energy harvesting devices, there's a common challenge that is the energy input from nature is unstable. The result are unstable output. But for small electronics, they usually need a stable power supply. To solve this problem, we still need to borrow the force from the batteries. The big battery has a regulation capability at the discharge plateau is always have stable electric output. But in order to improve the variability, so here we develop a fiber battery. So basically, we're using zinc as a well as an anode. So basically, those batteries could be biocompatible with this kind of silicon this kind of silicon encapsulation. We are showing that we can integrate this fiber battery into the clothes. So even during a bending or underwater situation, is always a very stable power supply. So we are just use this fiber battery as a kind of regulation capability and to provide stable electric output with the energy harvesting devices. So here's one of the solution. So we just hybridize this fabric solar cell with fabric batteries to integrate this photo rechargeable fabric. So it can overcome the limited lifetime, the disadvantage of limited lifetime of battery system. And so we can see that when there's a sunshine, so there's a photo charge situation, they can constantly generate electricity. So those generate electricity can immediately stored in the fabric batteries. So at the discharge platinum of fabric batteries, they can always have stable electric output. So with this kind of hybridization, you can see definitely with regulation capability of fabric batteries. So this fabric could work as a sustainable and a stable power source for wearable biomedical devices. So definitely, this is just a very proof of concept demonstration. So far, we are still working this direction and to improve the efficiency of both the battery system and also the energy harvesting system. So in the future, we can develop different types of devices to convert more types of energy on human body or in surrounding into electricity to construct this type of sustainable and stable power supply system. So let's come to the summary part of my talk today. Basics, my vision to the smart textile for the personal healthcare is that in the future we can develop different type test component which is able to integrate into a piece of a garment. So this type of garment, we can integrate different text sensors, power supply system, and also therapeutic devices. So if you have certain type of disease, maybe you just wear a certain type of clothes, so your disease will get treated. So still 3 months ago, the chemical review invited me to write another review paper talking about electronic textile for wearable point of care system. So it's also highlighted from cover of the journal. So if you are interested in this concept, you can read this paper. So it's very frontier, and definitely a lot of the concept here is in the stage of proof of concept. But I would like to say it's still very promising, and in the future, I hope in the near future, if you get some type of disease, you just wear some type of clothes, and your disease will get treated. So then come to the launch part of my talk today. Basically, I wanted to thank my wearable bioelectronics group at UCLA, including a number of postdoc and PhD students, and also the collaboration contributors, which made a significant contribution to the work I present here. And also, I would like to thank the funding agency as well. So thank you very much for your attention to my talk, and welcome you to UCLA. Definitely, Terasaki Institute is very close to UCLA campus. Welcome to stop by, and we can have a conversation and drink some nice teas from China here. Thank you very much for your attention, and I'm open to take any questions.
Thank you for this great talk, Professor Chen. Totally appreciate it. One question is, are you looking into implantable devices for your applications, for energy at least?
Oh, yes, definitely. This is a very good question. Yes, so definitely compared with wearable devices, the implantable is more challenging because you have to, in a human body, we have a lot of pressure over there, and also between organs, we have a lot of inner pressure, and also they have some biofluid. So yeah, so with the in collaboration with Professor Jun Chen and also Professor Sony, now we are shift our research focus to the implantable a little bit. So yeah, we are still wanted to harvest energy for heart beating in an implantable manner. So to drive some pacemakers. So yeah, so we are stepping through that direction. Yeah.
Thank you.
Yeah.
Another question came in. How can we separate piezo and turboelectric properties in a sensor that we have both of them?
piezo. So I don't quite get a question. So what?
If a material is both piezoelectric property and triboelectric property,
Okay, so
can you separate them and utilize these things separately?
yeah, sure. So definitely, those two platform technology, piezoelectric and triboelectric, they are totally two different platform technology. They have different materials uses, different structure design, and different output electric signal characteristics. For example, piezo definitely they have a much slower voltage and current output. The typical output of a voltage is several millivolt, and the current just several, even sometimes picoamperes. But for triboelectric, the voltage is very easy to be up to 1,000 volt. The current is typical on the order of several tens of microamperes. So basically, if you combine the two together for sensing, so I would like to say that the triboelectric devices will be dominant in terms of the output electric signal, especially for the voltage signal, at least 1,000 times higher than the piezoelectric. So that's why I don't quite understand this question. So how to separate the two? So I would like to say it's very hard to integrate the two into a single device for biomonitoring, and I don't see why we want to do that yet.
Okay.
Yeah.
Okay. Did you consider integrating antimicrobial textiles with smart textiles in healthcare application?
Yeah, sure. Yeah, definitely. This is a very interesting direction. So yeah. So we are showing that. So for antimicrobial textile, definitely the easiest way is just putting some silver particles onto them. They can kill some bacteria. But certainly we can use those generate electricity, especially for triboelectric platform technology that are able to generate high voltage up to 1,000 volts. We can use those high voltage to kill some bacteria as well. So definitely this is that could be promising. Yeah.
Thank you.
Yeah.
Are you looking into scalable manufacturing for your textiles? Some people look into roll-to-roll printing and others.
Yeah, definitely. Yeah, definitely. For all of the bioelectronics devices, if we wanted to bring in really society impact, definitely wanted to make it scalable, especially large scale for application. Yeah, we're always looking for those technology which is able to scale up our devices. Yeah.
Thank you.
Yeah.
Final question. From your point of view, what are the biggest challenges for wearable electronics for the next 10 years?
So definitely, yeah, I think a lot of wearable biomedical devices nowadays just in a proof of concept stage. So depends on different working mechanism. Definitely have different challenges over there. So for my type of study, basically they are trying to convert the biomechanical pressure into electricity and develop into wearable biomedical devices. In this direction, I think one of the problem that is how to make the devices is stable against the sweat or against the biofluid inside the human body. And another reason that there will induce a lot of motion artifacts. So actually, those devices are not able to convert the biomechanical pressure on human body into electricity, as I show you in one of the work. Actually, is able to convert all of the other type of mechanical pressure into electricity. So definitely, if you wanted to put them for clinical studies, so definitely you have to use some final device design or machine learning algorithm to get rid of those motion artifacts. And I think this is a big challenge in my field of study. So for some other wearable bioelectronics, for example, for wearable sweat sensors, so those I'm not convenient to comment their technology. Yes, so definitely different wearable bioelectronics depend on different materials usage, different working mechanism. They have different type of challenge over there. Yeah, but I think in the future, definitely those devices could be commercialized, and especially some, I cannot say most of them. I cannot say most of them, maybe a small portion of them could be commercialized, still on the way. Yeah.
Another question came in. Have you considered the integration of electrochemical sensors to sense bioanalyze in sweat into textiles?
Yeah, sure. Yeah, definitely. This is a very good question. So, so far, based on as far as I'm concerned, the majority of the textile biosensors are based on applied physics. So some of study, for example, one of the work published by Professor Hui-Shen Pen at Fujian University, they also develop a textile devices sweat sensor that are able to integrate those sweat sensors into a textile form to analyze the sodium concentration, global concentration in the sweat. They have this type of study. But I would like to say for electrochemical sensor, if you wanted to integrate into textile, there are more challenges over there because textile itself is a fiber shape and they have a lot of capillary force and a lot of microstructure over there. So the weakening of the fluid and also the absorption fluid and the chemical reaction site, actually they will become more complex compared with those thin film platform-based, this flat platform-based sweat sensor. Definitely there are more challenges over there. But yeah, but still there are some people working on the field. Yeah.
Thank you. Also, what is your favorite textile material? Do you play with cotton or polyester, or what are some of the materials?
Yes. So basically, cotton is one of the favorable materials because cotton is we have a lot of raw materials in nature and also is environmental friendly. But cotton, they have challenges of there because cotton is chemically inert and also is non-conductive, and especially the yarns actually is not very long. So if you wanted to make them a long cotton yarns, so definitely you have to use some specific technology. So that's definitely for cotton, they have advantage, disadvantages. Nowadays we are trying to use cotton fabricate some devices. Recently we use cotton to build up a wearable respiration sensors. We show that device definitely has a greatly improved wearability, wearing comfort compared with the other synthetic polymer-based textile devices. Yeah.
Thank you. One other question came in. Very inspiring talk. I was wondering which part of your technology are most promising for practical or translational applications? What is the major challenges hindering the translational application?
Yeah, so basically so far, I think the Magnetoelastic one, so that is one of my proudest research so far. And also I think that one is definitely gonna be more practical because it's intrinsically waterproof, and I see a lot of promising application over there. So yeah, this is my answer to this question. Yeah.
Thank you. Is your material capable of collecting EMG as well?
Oh, yeah. So EMG, the working principle definitely is different from our device. So our device is first is energy converter. So it converts the mechanical motion into electricity for biomonitoring. So EMG is different from another, use a different working mechanism. So yeah, definitely some of the materials could be used to fabricate the EMG. Yeah, especially some metal electrode over there. Yeah.
Thank you so much. Well, that's all the questions I have. Thank you for the fantastic talk, Professor Jun Chen.
Okay, thank you so much. Thank you, Mehmet and Ali and everyone here. Thank you for your time. So if you, in case you have a question and cannot ask me right now, you can shoot me email and I will be more than happy to keep talking with you over there. Yeah.
Thank you so much. Have a nice.
Thank you, Mehmet. Take care. Okay. Thank you, everyone.
Thank
Bye.
you.
Okay.